Have you ever stared at a piece of code you know is right, but it's just acting weird, illogically? Well, today, we're going to play detective. We're going to look at some C code that seems to straight up lie to us, and in the process, we'll uncover how a bug can actually travel back in time.
All right, let's get right into it. We're starting with something super common in C programming, right? Accessing an array. And to do that safely, what do? Well, you're going to add a check to make sure you're not about to write somewhere you shouldn't. And here it is. Looks familiar, doesn't it? We've got an array, A. It's got 5 slots, index 0 through 4. So before we write to it with our index x, we do the sensible thing. We check, is x less than 0, or is it 5 or more? If it is, we jump to our error handler. If not, we go ahead and safely write our 0. Seems bulletproof. I mean, this is day 1 stuff. But here's the twist. What if I told you that a modern, super smart optimizing compiler could look at this perfectly good code and just decide that your safety check is totally useless and just, poof, delete it? How on earth is that even possible? That's the mystery we're cracking today. So to figure this out, we need to introduce our prime suspect. And no, it's not a bug in the compiler. It's actually a core, deliberate feature of the C language itself. You can think of it as the compiler's dark bargain. And that feature has a name, undefined behavior, or UB for short. Now, the official C standard is very clear about what it is by being very unclear. It says it's behavior for which the standard imposes no requirements. What that really means is, if your code hits undefined behavior, literally anything goes. Your program could crash, it could spit out the wrong answer, or, and this is the really scary part, it could look like it's working perfectly fine, hiding the bug for another day. Now, you gotta understand, UB isn't some mistake in the language. It's a feature. It was put there on purpose for one big reason: speed, performance. By telling the compiler, hey, you don't have to waste time checking for stuff like array bounds or if a signed integer overflows, the language lets it strip away all that overhead to get maximum performance. And this whole situation creates a really important unspoken contract between you, the programmer, and the compiler. The compiler doesn't go looking for undefined behavior, it just trusts you. It assumes your code is perfect and has absolutely 0 undefined behavior in it. And this assumption, it's a huge deal. It's basically a license for the compiler to go wild with optimizations. Because it trusts that you will never, ever write out of bounds, that you'll never overflow a signed integer, it can rewrite your code in some truly radical ways, all in the name of making it faster. Okay, so we have our clues on the table, we have undefined behavior, and we have this contract where the compiler assumes our code is perfect. So let's put the pieces together and see how this makes a bug look like it can travel through time. We just need one more piece of the puzzle. It's called the as-if rule, and it's pretty simple. The rule says a compiler can mangle, rewrite, and totally transform your code however it wants, as long as the final result you can see, like what gets printed to the screen, is the same as if it had run your original code line by line. Okay, let's go back to our code. The compiler is chugging along, and it gets to that line, a of x equals 0. This is the moment. This is where it gets clever, maybe a little too clever. The compiler thinks to itself, okay, the programmer promised me no undefined behavior, and I know that accessing a of x would be undefined behavior if x was, -1 or 5 or 100. Therefore, and this is the big leap, x must be a value between 0 and 4. It deduces this as a fact. And that deduction has an absolutely shocking consequence. If the compiler has already decided, as a matter of logic, that x has to be in the valid range, what does it think about our safety check? It looks at x is less than 0 or x is greater than 5 and says, well, hold on. Based on what I already know to be true, this condition can logically never happen. It's impossible. And what does a good compiler do with impossible code? It gets rid of it. It optimizes it away. Your safety check, the one you wrote to prevent the bug, is completely removed from the program. A potential bug later in the code, the array access, has reached back in time and erased the very thing meant to stop it. That's time-traveling UB. So this is kind of terrifying, right? If the compiler can play these kinds of mind games with our code, how are we supposed to write anything safe and reliable? Well, this is where we need to change our mindset of it. We need to stop chasing every shiny new feature and start writing code that is, above all else, dependable.
The way forward is to be disciplined. Instead of trying to be clever and outsmart the compiler, we just don't go into those dark corners of the language in the first place. We adopt a philosophy of writing what's called dependable C.
You know, a really great way to think about this is newscaster C. A good newscaster doesn't use a bunch of weird regional slang or the trendiest new words. They use a clear, neutral, universally understood language so that everyone, everywhere, gets the exact same message. That's what we want for our code.
And this really highlights a key choice we have to make. Sure, modern C standards like C23 are rolling out cool new features, but they might not be supported on every compiler, and they can add new layers of complexity. Dependable C, on the other hand, is all about sticking to that core, stable part of the language that has worked reliably for decades, and will probably keep working for decades to come. It's about longevity, not novelty.
Okay, so let's get practical. What does this actually look like when you're typing away? Let's build a little toolkit of dependable habits and things you should probably just avoid.
Here's some really concrete examples. See variable length arrays? They can cause UB if you blow the stack. Just use malloc or a good old fixed size buffer instead. That new auto keyword in C23? Just skip it for now and declare your types explicitly. Int, double, you know the drill. And these newfangled ways to initialize structs? Nah, just initialize each member one by one. Sure, it's a bit more typing, but it is absolutely crystal clear to you and to every compiler.
Seriously, you should just burn these rules into your brain. Never, ever read from memory you haven't initialized. Watch those signed integers like a hawk so they don't overflow. Just say no to VLAs. Don't compare pointers that point to completely different blocks of memory. And please, remember that memset0 is not a portable or guaranteed way to create a null pointer. Sticking to these rules is how you honor that contract with the compiler and stay safe.
And all of this leaves us with one final big question to chew on. In this industry that's obsessed with the next new thing, this weird case of the time-traveling bug really forces us to stop and think. What is it that truly makes code good? Is it about using the absolute newest bleeding-edge tools, or is it about sticking to the most timeless, dependable, and trustworthy principles?